Welcome to the second session on mechanism design. The first talk of the session is on interdependent values without single crossing by Michal, Feldman, Amos, Fiat, Goldner, and Alon and
Hi, I'm Alon. I'm going to talk about interdependent values in the situation where you don't have single crossing. This is a joint work with Michal and Amos, and we were very fortunate to have Kira with us as well in Tel Aviv. So let's start with the question. How much would you be willing to buy this picture for? How much would you be willing to pay for this picture? Any suggestions? $50. Great. How about this one? Somebody knows? Okay. So apparently, the first one you can buy online for $86, while the second one you would have to sell a kidney or something or more. Because it's a park piece and it's worth $140 million. And what's interesting, like for someone like me that doesn't understand art, these two look abstract and colorful, and I wouldn't have any idea which is more valuable. But if I have some more information of the experts who know art, I would know that this is a park piece. And those of you who are familiar with this piece would know this should be upright. And those of you who are experts would know this is still upside down. So this is the correct place note for. So this is what interdependent valuations stand for. They try to capture settings where your value, you don't know your own value. It depends on many other, much more information. So let's, in this talk, I'll talk about the most fundamental problem in game theory, just allocating a single item to the bidder values it the most. And most of you think it's already solved, right? We have a second price auction. But this solution only works when players know their own values, and in this setting, players don't know their values. So more formally, what's the setting? So each bidder has some piece of information, some signal Si, but his value, his public valuation function, who is known for all, is a function of all the private signals of all the bidders. So if I have a valuation function, it maps the entire data of all the players to some real number. Okay. And because it captures some correlation, it might as well be drawn from some correlated and joint distribution. Here's a simple demonstration of such a function. You can think about my value is for something is the average of my signal, my estimate, and yours estimate. Okay. This dependences arise in many settings. For instance, you can think about artwork as we discussed, that my value also depends on the data of the experts and the dealers and all those, or spectrum licenses, or maybe oil fields where each one might have some estimate for the amount of oil. And if you know that there's a lot of oil in the field, I'll probably value it more. Or maybe also the job market. So there are many examples. So let's be more specific and give some concrete and simple example that was given by Dasgupta and Raskin. So there are two oil companies who want to drill some oil field. And oil has a price of $4 per unit of oil. And only one of the companies, only one of the drillers has some estimate of the amount of oil. Run some tests and has an estimate. And this company has a fixed cost of 1 for setting up the oil site and a marginal cost of 2 for every unit of oil it sells. So his value for the field is 4, the price you will sell the oil, minus 2, the price for production, minus 1, which is the fixed, times the amount of oil in the field, minus 1, which is the fixed cost. And there's another driller which has a fixed cost of 2 and marginal cost of 1, so his valuation is 4 minus 1 times the amount of oil in the fields, minus 2. So this is very, very simple. Both of them depend on only one player's signal. Okay. What is the mechanism in this system? So when you know your value, you bid for your value. Here, you bid for your signal. Your private data is your signal. It does a public valuation function, and the only private piece of information you have is your signal. So bid on a signal, and according to all the bids of all the players, you have some probability to get allocated and some price for the that you have to pay. So for instance, here's a two players case. One has 4 passable signals, one has 3 passable signals, and for each combination of bids, we can say who is the winner. For instance, if the red player, player 1, bids 1, and the blue player bids 1 as well, then the winner is the red player, because in this cell 1, 1, we decide to allocate 1. Okay, so we know how a mechanism looks like. So what is a truthful mechanism? So in the private value model, if the private data is your actual value, you know your own value, we already said that we have the second price auction, which is has many desirable properties. It's deterministic, it's dominant strategy instead compatible, and it's power-free, meaning that we don't need to reason about the details of the distribution in order to get the optimal allocation. But with interdependent, it's easy to see that we can't implement a dominant strategy mechanism because I don't know my value. So if you report some arbitrary signal, it's not clear I should bid my true signal because I don't know what the picture was to me. So the best thing we can offer is something called ex post IC, which basically means that if other bidders bid their true signal S minus I, my best response, the best thing for me to do is bid my true signal SI. And we also require a standard ex post IR. So in this talk, when I say truthful, it's ex post IC and ex post IR. Okay. And a nice analog characterization to Milestone's characterization was given by Ralph Gardner and Talgan Cohen. And they said that the mechanism is truthful if and only if my allocation probability is the monotone in my signal. And they also gave some analog of the payment identity. So what does it mean by monotone? What do I mean by monotone? So for any fixed bid of other signal B minus I, my probability to get allocated xi increases monotonically non-decreasing in my signal bi. For instance, this is a monotone allocation function because, as you can see, as the red agent starts winning, if it increases signal in the x-axis, it keeps on winning, and the same for the blue bidder. If we increase the signal, it's still the winner. And this is a non-monotone function because you can see in this cell, when we increase the bid, we are no longer the winners. Okay. Part of the this is a two-player case, so it's just a matrix. But when we have more than 2 players, this is a hypergrid. So one of the main challenges of this work is finding a monotone corollary of a hypergrid, basically, that gives us good approximation guarantees. Okay, any question about the model? Okay, great. So previous work considered the single crossing notion, which basically means that my sensitivity to my signal is greater than your sensitivity to my signal. Which means that if I increase my signal, my change in value is greater than yours. This can be formulated by some conditional derivatives, for instance. And to depict how it looks like by diagram, we have the signals of the red pairs increasing. You can see that the slope of the red value diagram is larger than the blue value diagram, which basically means that once the red diagram crosses the blue diagram, they won't cross again because the red increases more fast than the blue one. This is why we have the name single crossing. Okay. And the reason they looked at single crossing is because with single crossing, we can implement the maximum value allocation. Because it's easy to observe that single crossing implies that allocating to the max bidder is a monotone in its signal. And we already said that an allocation function is monotone, implies that it's also implemented by a truthful mechanism. And a generalization of VCG can be defined accordingly. So basically, all previous work considered some notion of a single crossing. And there was a good reason because it was observed that without single crossing, there is some example where we can't implement opt truthfully. We can't allocate to the max bidder truthfully. So a natural question we ask is, what about approximate efficiency? If we can achieve efficiency, full efficiency, about approximate guarantee to the world flow. Okay, so here's a simple observation. if we shoot for something that is power-free and deterministic, we can't have any guarantee. It could be really bad. Consider this really simple instance where only the red player has 2 signals and the blue player has 1. So when we look at the bit profile 0, 0, we must allocate to the red player because the blue player doesn't approximate the red player to a factor of r. So we allocate to the red player. And because we, unfortunately, truthfulness means that we also need to have a monotone allocation, so we have to allocate to the red player here. And you can see that in this cell, the blue player, the red player does not approximate the blue player. Okay, so you can say, okay, this is deterministic. Maybe we can run some randomized mechanism, and the answer is also, unfortunately, if there is some instance without single crossing in which every randomized mechanism, even if I give you the priors, you can get better than n approximation. Any idea how to get n approximation? Anyone? So we just can allocate to a random bidder and get n approximation. So this seems really bad, right? This seems hopeless. So what our solution is in this case is to say, okay, the world is not just single crossing or not single crossing. There is some spectrum of evaluations. We can ask for relaxed single crossing, for instance. And how do we define relaxed single crossing? So it's almost the same condition, but with a C, which means that my signal is not insignificant to me compared to you. If I increase my signal, my change in value is at least 1 over C, the change in your value. Okay. There's a reason I have this signal, basically. So before the picture was like this, there was the valuation who maintained single crossing and the ones that did not. And we offer a spectrum of, given a valuation, we can ask what is the small c for which this valuation profile is C single crossing. And we can ask what approximation can we get for, let's say, 2 single crossing valuations. Okay. And the reason I brought up the oil field example before is because it was a really simple example in which the scoop sign masking showed that single crossing can be violated in really simple settings, really simple and realized setting. So in this example, you can see it's not single crossing, but it's 1.5 single crossing. So what can we say about this example? Okay. So let's start talking about our results. Let's start with the 2 simple case where we have either 2 bidders or 2 signals. So for 2 bidders and any number of signals, there is a deterministic and prior free mechanism that gets us C approximation. And I remind you that without single crossing, this is unbounded. And this mechanism gets the best factor for deterministic mechanisms. How about the case of any number of bidders, but each bidder has 2 signals? For this case, we can also get a deterministic power free mechanism that gets this C approximation. And before that, we had n lower bound, even using randomization and even with priors. Okay, so this is a major improvement. We got C in both. And you might think we can get always can get C, but okay. Okay, let me talk about the mechanism a bit. So the first one is just, because we have 2 pairs, the bit space is just a matrix. So we found a way to color the matrix in a way that is C approximation everywhere. And the case of n bidders and 2 signals is just a hypercube. And we found a monotone allocation, a monotone coloring of the hypercube that gives this approximation. And you might think that we can always get C, but the answer is that there is an example with 3 bidders and only one has more than 2 signals in which we cannot get C. So C is not always the right answer. And more general results that we have is that if we consider any number of bidders and any number of signals, we can show an n-1 C approximation in polytime via deterministic and prior free mechanism, which doesn't seem exciting, but it's still better than unbounded that we had even for 2 pairs. And how about a randomized mechanism? So it turns out that a randomized mechanism, or a variant of the same mechanism, gives us an improved bound of 2 squared n times C to the 3 hat. And this is again better than the n lower bound we have without single crossing. And we also, in an ongoing work, are considering other notions of relaxation that removes the dependence on n. I won't talk about it too much. And I won't talk about the deterministic mechanism. It's also some coloring of a hypergrid mechanism. So how does the universe look like of the interdependent variations? Okay. So we know that if we consider the class of all interdependent variations, we have some hard instance in which no deterministic mechanism can get any bound. And we have another hard instance in which no randomized mechanism can get better than n. And Simon crossing was offered by economists to give us a class of variation in which we can implement opt. And we extended it to C-sim crossing a class which avoids these two best points. And in recent work, we also considered concave variations. What's interesting about concave variations is that they can perform really bad deterministically, but surprisingly, we perform really good with a randomized mechanism. And we can also relax this notion and get some nice bounds, and we can also get some positive results even for revenue maximization, which I won't talk about. Okay, so natural open questions is we have some bounds that show we can improve upon the worst case without sin crossing, but they are not tight. So maybe we can remove the dependence on n with system crossing variation. And you can think about other setting of interdependent valuations in which maybe we can get up, but what approximation makes sense. And last question, which of these is the correct one? Anyone? Okay. Thank you.
Right, so any questions? So let me ask you one question. So all of these results were for the prior free case. If you allow some limited dependence on the prior, is there any of these bounds that can be broken?
So one of the lower bounds was with the priors, the randomized one. So for randomized mechanism without sin crossing, we can't get anything even with priors. But the upper bound might use some information. We didn't look at that. Okay.
Thank you. Any other questions? Okay, let's thank the speaker again.